some partition element is gonna deal with 1. If 1 is the left endpoint, if 1 is the left endpoint, then the contribution is 1. If it's the right endpoint, what is it? Contribution 0 then, right? I have a skinny little rectangle that I have to somehow cover the point 1 with. So slide that thing around and ask yourself what happens to the Riemann-Stieltjes sum. And if I slide it all the way over here, then f is 1 and delta alpha is 1. So with that, if you push him all the way to the right, it's 1. If you push him all the way to the left, then what happens? It's 0, it's still 1. It's all the way to the left. See, if you use 1 as a tag point, you get this bump of 1 in the integral. If you don't, suppose this is the macroscopic situation here. Suppose the point 1 is here, right? So alpha and f are changing there. What if you pick the tag point there? Then f is 0. You pick him over there, he's 1. And if delta alpha is 1, you can either have a 0 or 1. And this guy here can be really, really skinny, right? As long as he encompasses 1. The bump, depending on which side of 1 you're from. You see that? Depending on which side of 1 the tag point is, the contribution to the integral from 1 to 2 will either be 0 or 1. And you can make the width of that element arbitrarily small. So you can make the partition arbitrarily fine. And you still have a lump of 1, a macroscopic lump, that separates the two Riemann-Stieltjes sums. Which means they're not approaching a limit. Which means the limit doesn't exist. Which means the Riemann-Stieltjes integral doesn't exist. Okay with that? That's kind of weird. Now, why is it not true for just a Riemann sum? Thank God that doesn't happen with the Riemann sum. Oh, by the way, can we impose a condition here about these jumps? What if alpha were continuous? Could this phenomenon happen? No. Were you here, Dave, when we talked about Lec functions?
Yes.
What if they're cool? Huh? Continuer à droite, limité à gauche. Yeah. Right.
I memorized that.
Did you really? Wow. God bless you.
I know these like little things in there. I'm trying to figure out what I can get off of. I need to be sneaky.
Well, I'm not that sneaky. Come on. All right. So if we assume that alpha is continuous, even if f is not, then the delta alphas aren't lumps anymore. So it doesn't matter how f is bouncing. F could be discontinuous. F can be bouncing around all over the place, but the contribution of the delta alpha will not be macroscopic. Right? If it gets small enough, not much contribution. The problem here is the partition can be very fine if delta alpha is still 1. So it overemphasizes what f is at that place. Okay? All right. Good. I want to try to explain that. A fact about monotone functions that Burke is interested in. You perhaps read about in chapter 3. Theorem. If f is monotone, f has at most infinite type 1 discontinuities. I didn't leave myself enough space. That's discontinuity. Okay, I better stop. We're broadcasting. I better write that up. Discontinuity. There we go. Yeah, f has at most countably many type 1 discontinuities, which means, what's a type 1 discontinuity? Or removed. Here's a better way to remember. If both lateral limits exist, but a function is discontinuous at a point, then that's type 1. Any other situation is type 2. Right? So what can happen if both lateral limits exist? Well, the function may or may not exist there. That's a possibility. That would be a removable one. If it doesn't exist, you can, right? You could, if the lateral limits are equal, but there's a hole there, you can just define the function to be what the common limit, then you compare the discontinuity. The function value could exist, but the lateral limits are different, right? Or the function could be different than the common lateral limits. You can move it. So you have the jumps or the removals. What's a type 2 discontinuity? Like the salt and pepper function, right? Every point of the salt and pepper function is a type 2 discontinuity. Here's a test question for you, pop quiz. Please design a function that has a type 1 that's continuous at 0 and has type 2 discontinuities everywhere else. No. Yes. Okay, that's good. The one I'm thinking of. Just want to make sure. Continuous at 0, type 2 discontinuity everywhere else. Type 2 everywhere else. So all the other discontinuities are either removable or jumps. Yeah. And the winter is. Oh, I wrote that wasn't on. I thought you were going to answer. How did we make
I think it's obvious.
it is really. How did we make x sine 1 over x continuous? You know, the x, right? Sine 1 over x is very poorly behaved at 0. It's continuous everywhere else at 0. Sine 1 over x, if x is not 0. 0 if x is equal to 0. So that's a discontinuous function at 0. Badly. The sine is oscillating infinitely fast, but the function at 0 is just 0. In any neighborhood of 0, you will find values of x such that the sine of 1 over x is plus 1 and minus 1. It's worse than that. In any interval, you'll find infinitely more. X is more than it's true, right? What if you had
about if f of x is equal to the absolute value of x if x is irrational, equals 0 if x is irrational.